All right, so where are we here? Removing duplicates from a list. So remove dupes. So what this is meant to do, they don't have to be numbers, they could be like letters. But the idea is I'm given a list, and it may have the same number might occur. Someone was asking about this. You can have the same thing occurring multiple times in the list, and the idea is it should remove all of those duplicates and just keep one copy of each item. And it's actually the last occurring one that's kept. So all the other B's are removed and only the last one remains. Yeah. Can everyone see that? So how would you write a program to do this? Well, first of all, what's the base case? What's the simplest case? One item? Yeah, you could write it with one item, but actually there's an even simpler base case than that, 0. Yeah. So if the original list is empty, the new list will also be empty. Okay, so that's the base case. Now here we need 2 recursive cases. What are the 2 recursive cases? Right. Right. So you look at whether the first item occurs in the rest of the list or whether it doesn't. And this is where we're using this built-in function member. So this rule is saying if the first item is a member of the rest of the list, then that means we don't need this item because it occurs somewhere else. So we just remove dupes from the rest of the list, and whatever comes back, we return that. Right? Now, what happens if the first item is not a member of the rest of the list? That means we need this first item because it's not going to occur again. So we still remove dupes from the rest of the list, but then when we get back the answer, we have to put this first item back on the front because we still need it. And notice the not here. So not member first rest means it has to try to prove this and fail. Right? So if member first rest comes back as false, then not member first rest will come back as true. So let's remove dupes, A, B, C, D, F, G, A, C, F. And if we trace it, you can see what's going on. You can see whether member succeeds or fails. I won't go through all the details, but you can step through this yourself and see how it's arriving at the answer. Variables in a Prolog program usually occur more than once. If you look at all the Prolog programs that we've written so far, you see how first occurs here and then occurs here. Rest occurs there and there and there. So normally the variable, you get the value of the variable somewhere and then you use it somewhere else. So it's quite rare that a value would occur only once. And for that, it's so rare that the compiler, if it sees a variable used once, it assumes that you've probably made a mistake. Maybe it occurs twice, but you've spelt it wrong. Or maybe you've left out a piece of your code or something. So it'll come back with a warning. But there are some rare cases where we do actually want something to occur only once. So for example, with count item, if you look at this rule here, this says that if you're looking for a particular item, this is code it's given an item and a list, and it counts how many times that item occurs in the list. And the base case says that if you're looking for an item in an empty list, it occurs 0 times. It doesn't matter what the item is. So the compiler will actually give you a warning here. Now, so it's important when you submit your assignment, you must write your code in such a way that it doesn't give you any warnings. So the way we get rid of this particular warning is we put an underscore in front of that name. So if we put an underscore, we could just write the underscore itself, or we could write underscore and then a name. But this tells the compiler, yes, we're aware of the fact that this is a singleton variable and we want it to be a singleton variable because we don't care what its value is. So you put in that little underscore here, and then the program won't give you that error, right? So that's just an element of style that we insist on. Okay, and then the last the last topic here is about cuts. So the cut is an operator that you can put into your code, and it kind of controls the execution or prevents, cuts off the search, and it's a little bit of a mysterious element of Prolog. So without the cut, Prolog is a very kind of logical and elegant mathematical language, but then when we put the cut in, things start to happen which aren't sort of fully in line with abstract logic, but sometimes we need cuts to make our program work properly. So here's an example of a cut. Let's say, so we go back to our facts file, and if I say lectures cod X, if you remember, this comes back and tells us that these are the two courses that cod is lecturing. And if I also want to say studies YX, so which students is cod actually teaching? We went through this in the last week's lecture. It comes back and gives answers. So X could be 9311 and Jack, or it could be 9314, it could be Jill or Henry. Now, if I put this exclamation mark in there, this is called a cut. Now what happens here is it says, okay, once you've found, it first looks at what's before the cut and tries to assign values to these variables, including X. So it says, okay, X can be 9311, and then it passes through the cut. And then when it gets over here, X is equal to 9311, and it looks for a student. It's not allowed to go back and try a different value for X. So that's the meaning of the cut, is it can't try a different value for X. Whatever value it had for X is locked in, and it can't try anything else. And additionally, if there's some other rule for lectures, it's not allowed to go back and retry that either. Thing you can actually see this graphic. It just cuts off the last part of the search, right? So it's not allowed to, it's found a value here and it's not allowed to try any alternate values. Now, I was just playing around with this. I think if I edited this facts file, I mean, the one that it comes up with is the first one that's listed. So if I actually put these in the other order, it would find cod lecturing 9314 because it would search the thing in the other way. So now if I say lectures cod X, it's 9314, and if I say studies student X, right, sorry, and then I put the cut in, it comes out with two answers. So the cut doesn't force it to come back with only one answer. So what's happening here is it's searching from this side, and the first one it finds is 9314, and then it finds that the student could be Jill, and then it's allowed to try another student, which is Henry. So because the student appears on this side of the cut, it's allowed to try multiple values for student, but it's not allowed to try any other value for X because X occurred before the cut. So yeah, it's a little bit, the cut is a little bit confusing, but that's the way it works. So that anything that's on the left side of the cut is fixed, but things that only occur on the right side of the cut, you can still try multiple values. Yeah?
Can we cut also the right side to try just one value?
You could put a cut at the very end, and then it can only come up with one answer. Yeah. Okay. So that's we're just going to show you a couple of examples of this, okay, and then we'll so they tried to put this explanation here before the cut and after the cut. Okay, so the first example is max. This is a rule that will find the maximum of two items. Finds the maximum of the first two items and returns it as the third item. So I can say the first rule says that if A is greater than B, then the max of A and B is A. The second rule says that if A is less than or equal to B, then the max is B. So this is perfectly good code. Now we could rewrite this with a cut by saying the first rule here says if A is greater than B, then the max is A. And then we put the cut in. So, and then for the second rule, we just simply say max A, B, B. So the way this works is it first tries to test whether A is greater than B. If A is greater than B, it returns A, and the cut prevents it from moving on to the other rule. So the cut prevents it from trying any other rule for the same predicate. So once it's got to the cut, it's not allowed to come down and use this rule. But if A is not greater than B, then this rule will fail, but it's allowed to come down to this rule. So these two actually produce the same answer, but one of them does it with a cut. Now, it's kind of, usually we regard this as a kind of bad use of a cut, because this code is easier to read and only slightly longer than this, right? But this illustrates the way the cut works. Now here's another example from last week. Remember, we were looking at whether one date is later than another. So we had these three rules. One covers the case where it's the same year and month. One is where it's the same year but a different month, and one where it's different years. Right? Now, logically, these rules actually exclude each other. If one rule succeeds, the other two are guaranteed to fail. You can, if you figure it out, that's actually logically true. But sometimes people say, well, I want to make sure that only one rule succeeds, so I'll put a cut here and a cut here. So I guess what I'm saying is that when you first start writing Prolog code, you feel this urge to sort of put cuts all over the place, or your code is not working, so you think, oh, maybe the solution is to put a cut here or there. You can kind of cut your code to death. But you should try to avoid that temptation, because if you have too many cuts, it's really hard to figure out what's actually going on. So normally we try to avoid cuts where possible. Now, this last example is a case where a cut perhaps is justified. So this is going back to this remove dupes. Right, so this was the code we looked at before, and this is the code with the cut. Now what happens here is you think about, so again, someone was talking about having really long lists, right? Will the thing ever run out of memory? So let's imagine there's 1,000 items in this list, and it comes in and asks, is this a member of that list? So it has to check through 1,000 items, and no, it's not a member. So then this rule fails. So then it's okay, well, I'll move on to this rule. And the first thing again is it again repeats the same process of trying to check whether this is a member of that list. And I want it to not be true, and then I can apply this rule. So it kind of repeats this computation. So we can avoid that by putting in this cut. So what happens here is this rule tests whether the first is a member of rest. And if it is, then it does this. And because of the cut, it's not allowed to try that rule. If this is not a member, then it's allowed to come down to this rule, but it doesn't have to repeat the computations it just did to figure out that it's not a member. It just immediately applies that rule. So if you run this on a list of unique items where no item occurs twice, this actually speeds it up. It roughly doubles the speed, because otherwise you'd have to be doing this twice. So a computation that previously took 10 seconds will only take 5 seconds. So that's, in that case, if it's a very long list. So in that case, we treat it as an acceptable use of a cut, because it doubles the speed of the program with only one cut. Yeah?
In the example with
Yeah.
Why do we go to search students if we have a cut?
The cut, so there's two things about the cut. So the first thing is it's not allowed to go back and try different values here. But secondly, it's not allowed to go back and try to use a different rule. The cut prevents it from trying to use a different rule. That's what we're relying on here. So with the students, there wasn't another rule to use. It was just a matter of the variable. So the x occurred before the cut, so its value was fixed, but the student occurred after the cut, so it could try different values. I know it's confusing. Like a break in, yeah, that's a good analogy, like a break in C. But also like it's considered bad style unless it's really go to. So I think that's where are we? Oh, the dupes, right. So I'll just show you these different versions. So dupes cut, that's the dupes with the cut. So you can test the dupes with the cut and without the cut, and it speeds it up. You know, you can test that out for yourself. But this is another issue that I think is kind of interesting, is this slow version of dupes. So that's the original dupes, and this is the slow version. Now, can someone tell me what's the difference between, apart from the cut, what's the difference between these two versions? So look at this rule and this rule. What's the difference? Changing the order. So here we first test whether this is a member, and then we do the recursive call of removing the dupes. Here we remove the dupes first, and then afterwards test whether it's a member. Okay, so let's just run this and see what happens. So remove dupes A, B, C, D, E, F, G, X. That was pretty quick. H, I, J, K, L, M, N, O, P. That still was pretty quick. Q, R, S, T, U, V. Now it's starting to get a bit slow. You see that? How long was that? 10 seconds or it starts to get, every letter that I add starts to get noticeably slower. So why is this version very slow? Maybe have a think about this. And in fact, if I do W, X, Y, Z, it might not even, if I did 100 items, it may not, it might take a year or something, I don't know. So maybe this is, I don't know whether, maybe just have a think about this and we can talk about it next week. But why is it that all I've done is change the order of these things, yeah? Yeah, I don't think it's, well, it removes the dupes first, and then checks afterwards, and then it finds, in this case, everything's unique. So this is bound to fail, and then it does remove dupes. So if the original list is 30 items, it removes the dupes from 29, but then that fails. And then it removes from the 29 again, and then the 29 will remove it from the 28. And yeah, if you figure it out, this actually, the time is actually proportional to 2 to the power of the number of items in the list. Yeah, it's actually a very, very slow, it's like, the analogy with the carpet, I cut my piece. I have a carpet of length 30 and I cut one piece off, but I give the 29 to 2 different guys. And then each of those guys cuts their piece off and gives the 28 to 2 different guys. And then 27 is 2 different guys. So actually, if you figure it out, it's actually like the computation time actually doubles every time you add one item to the list. Just have a think about that. Yeah. All right. So any questions about the Prolog? Okay. So if you're a bit confused about this, just have a look at the video and work through those exercises. If you can get through all the exercises, you're in good shape.